Good morning, students. In today's lecture, we will talk about the theories which were used to explain bonding in coordination compounds. Bonding between ligands and the central metal atom or central metal ion. Four theories were proposed for explaining the bonding between ligands and the central metal atom or central metal ion. The most traditional is valence bond theory of VBT. It's having some limitations. That's why crystal field theory were proposed, which is called CFT. Again, it is having some limitations. So one more theory was proposed, that is ligand field theory. Again, it is having some limitations. That's why one more theory was proposed, that is molecular orbital theory. So total four theories are there, which explains the bonding in coordination compounds. In our syllabus, we are having only two theories, that is valence bond theory and crystal field theory. Ligand field theory and molecular orbital theory, that is MOT, is not in our syllabus. So we will talk about only VBT and CFT. Now let us begin with the valence bond theory. According to valence bond theory, between ligand and central metal atom or central metal ion, coordinate bonds are present. So here we can say that valence bond theory gives covalent treatment to the bonding present between ligands and the central metal atom or central metal ion. What ligands are doing? Ligands are contributing their lone pair of electrons in the vacant orbitals of central metal atom or central metal ion. It means central metal atom or central metal ion must have sufficient number of vacant orbitals in which ligand molecule can donate their lone pair of electrons. As a result of which, bond can be formed between ligand and the central metal atom or central metal ion. But before donating the lone pair, or in other words, central metal atom or central metal ion, before accepting the lone pair of electrons from ligand molecules, undergoes hybridization. Hybridization is a process in which orbitals having slightly different energies undergoes intermixing, as a result of which redistribution of energy takes place, and we obtain hybrid orbitals having same energies. So before bonding, hybridization is there in the vacant orbitals of central metal atom or central metal ion. These hybrid orbitals are more stable than the atomic orbitals, and these hybrid orbitals have definite geometries. Now when hybrid orbitals are formed, then in the hybrid orbital, ligand will donate its lone pair of electron. Now, if the intermixing of energy takes place between 1s and 3p orbitals, s only one, p 3 orbitals are there, then we obtain 4 hybrid orbitals having character of sp3, 1s and 3p. undergoing intermixing of energy. So in total we will obtain 4 sp3 hybrid orbitals which have geometry of tetrahedral. If sp3 hybrid orbitals are there, then these hybrid orbitals are arranged in tetrahedral pattern in space. Now, if 1d, 1s and 2d, how many from d? 1. How many from s? 1. How many from p? 2. So again, there are 4 orbitals which are undergoing intermixing of energy. As a result of which, again we will obtain 4 hybrid orbitals, that is dsp2. When 1d, 1s and 2p orbitals undergoes intermixing of energy, we obtain 4 dsp2 hybrid orbitals. And if hybridization is dsp2, then the geometry of the molecule will be square planar. Then what about with 6 ligands? If 6 ligands are there, we will need 6 vacant orbitals in the central metal atom or central metal ion. In that case, we are having 2 possibilities. And the possibilities are 1 from S, 3 orbitals from P, and 2 orbitals from D can undergo intermixing of energy, as a result of which 6 sp3d2 hybrid orbitals are produced. 6 sp3d2 hybrid orbitals are produced, and geometry will be octahedral because we are having 6 ligands. We have one more possibility here, and in this case, inner d orbitals like 2 from D, 1 from S and 3 from P undergoes intermixing of energy, as a result of which we obtain D2 sp3 hybrid orbitals. There is a difference in sp3 D2 and D2 sp3. In sp3 D2, outer d orbital is involved, and in D2 sp3, inner d orbital is involved in hybridization. But in both the case, geometry will be octahedral. So let us see how the hybridization takes place in first octahedral complex, that is COF6-3. Before finding out the hybridization, we must know the electronic configuration of the central metal atom or central metal ion. In COF6-3, the oxidation state of cobalt is +3. Reason is very simple. Each F is having -1 charge. It means due to 6F, you will be having -6. -3 appears on the complex ion. When it will appear? It will appear when cobalt is having +3 state. So in COF6-3 complex ion, the oxidation state of cobalt is +3. Cobalt, its atomic number is 27, so its electronic configuration is 3d7-4s2. Now for CO+3, we have to remove 3 electrons. So 2 electrons will be removed from 4s and 1 electron will be removed from 3d, as a result of which we will obtain electronic configuration of CO+3 ion as 3d6-4s0. There is no electron in 4s. There are 6 electrons in 3d. Now orbitals of CO+3, 3d, then 4s, then 4p, then 4d. This 4d is called outer d, and this 3d is called inner d, which is inner to valence. And if d is from the valence shell, that is called outer d. So here we are having 6 electrons in 3d, 1, 2, 3, 4, 5, and then 6 pairing is here. How many ligands are there in COF6-3? Definitely there are 6 ligands. Each ligand will contribute lone pair of electron in the vacant orbital of CO+3 But before accepting the lone pair from F minus ion, orbitals of Cu plus 3 or vacant orbitals of Cu plus 3 will undergo hybridization, intermixing of energy, as a result of which orbitals with same energy will be produced, which are called hybrid orbitals. So in total we require 6 vacant orbitals. So here we are having 6 vacant orbitals. 1, 2, 3, 4, 5, 6. So 1 from 4s, 3 from 4p and 2 from 4d will undergo intermixing of energy, as a result of which we will obtain 6 hybrid orbitals. Of which type? sp3d2 type. This is sp3d2, this is sp3d2, this is sp3d2, 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 sp3d2. Remaining 3 will not participate in hybridization because these are not required. We require only 6 vacant orbitals, so only 6 vacant orbitals will undergo hybridization, as a result of which 6 sp3d2 hybrid orbitals produced. So it remains as atomic orbital, but here we are having 6 sp3d2 hybrid orbitals. Now, in the hybrid orbitals, F minus ion will contribute its lone pair. So lone pair from first F minus, lone pair from second F minus, lone pair from third F minus, fourth F minus, fifth F minus, and sixth F minus. Clear? Because 6 ligands are there, so geometry will be octahedral. Now about the magnetic character. If central metal atom or central metal ion contains unpaired electrons which are not paired in orbitals, will be attracted towards the magnetic field and it will show paramagnetic character. If unpaired electrons are there in the orbitals of central metal atom or central metal ion, then it will be paramagnetic in nature. So what will be the magnetic property? It will be paramagnetic in nature. Now, because outer d orbitals are involved in hybridization, so this complex is also called outer orbital complex, and all the outer orbital complex are also called high spin complex because spin pairing has not taken place here. Electrons are unpaired. It will give rise to some spin. Now, next one is again your octahedral complex where F minus is replaced by ammonia molecule. So here as a ligand we are having ammonia. Now oxidation state, ammonia is neutral in nature. So whatever the charge is there on the complex ion is due to oxidation state of cobalt. So here also cobalt exhibit +3 oxidation state. Atomic number of cobalt is 27. Configuration is 3d7 4s2. So Cu plus 3 ion will have configuration as 3d6. It will be 0 here. It will be 0. 4s 0. Now orbitals of Cu plus 3 ion same as we have drawn in case first. Now about the hybridization. Here in orbitals of Cu plus 3 ion we are having 4 unpaired electrons. But magnetic susceptibility experiment has proved that there is no unpaired electron in this complex ion, or the magnetic moment which depends on number of unpaired ion, which depends on number of electrons, number of unpaired electrons is 0. If we are obtaining value of magnetic moment as 0, it shows that there will be no unpaired electron present in central metal atom or central metal ion. So according to magnetic susceptibility experiment, its magnetic moment is 0. It means it will not have unpaired electron, but here unpaired electrons are there. So what VBT is saying? According to VBT, we will carry out pairing of electrons in 3D. So here this electron will be paired with this one, and this electron will be paired with this one. So now we will get electronic configuration as in first we are having two paired, in second we are having two paired, and then two paired. So here it will be vacant because electron this is shifted here and this electron is shifted here, giving you two vacant orbitals in 3D. Now for accommodating 6 ns2 ligand, we require 6 vacant orbitals. 2 vacant orbitals are produced from 3D due to pairing. 1 from S and 3 from P will be utilized in hybridization. So here you will obtain 6 hybrid orbitals having character D2sp3. 2 from 3D, 1 from 4s and 3 from 4p will undergo energy intermixing, then redistribution, as a result of which we will obtain 6 D2sp3 hybrid orbitals. Now what will happen? NS3 ligand will contribute its lone pair in the vacant orbitals for the formation of coordinate bond. So lone pair from first NS3 molecule, lone pair from second NS3 molecule, lone pair from third NS3 molecule, lone pair from fourth NS3 molecule, lone pair from fifth NS3 molecule, and lone pair from sixth NS3 molecule. In this manner, we can explain bonding in CONS6 plus 3 complex ion. Now here 3D, which is inner to valence shell, is used in hybridization. That's why this complex is called inner orbital complex. No unpaired electrons are there. You know it very well that electron which is exhibiting clockwise rotation having spin plus half, plus 1 by 2, and for anti-clockwise rotation it is having minus 1 by 2. So plus 1 by 2 will cancel out minus 1 by 2. So here total spin will be 0. So it is also called low spin complex. It is called low spin complex. In the similar manner, we can explain hybridization in the complex ion or the coordination compounds where 4 ligands are there. If pairing is not there, you will get sp3 hybrid orbitals, and if pairing does take place, then hybridization will be dsp2. If the hybrid orbitals are sp3, then for the 4 ligands the arrangement will be tetrahedral. And if the hybrid orbitals are dsp2, then the arrangement of ligands around the central metal atom or central metal ion will be square planar. All the ligands will be arranged at the corners of the square. So this is how we can explain bonding through VBT in complex ion or coordination compounds. That's all for today. Thank you. Have a good day.